Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is change of bases matrices, matrices that we use for going from one basis of a vector space to another for changing bases. So let's start with an example. So let's say that V is R4, and we have this set B of 4 vectors in R4. Each one of these is one vector at a 4-tuple in R4. And this happens to be a basis for R4. You would have to check that, but take my word for it. Let's say this vector 47, 2 minus 1, 8 walks through the door, and you want to write it as a linear combination of these basis vectors. So that means that you want to find the coordinates of V, the coordinates of this vector, with respect to that basis. Finding the coordinates of V with respect to B means finding the scalars, alpha 1, alpha 2, alpha 3, and alpha 4, so that if you multiply this one by alpha 1, the first vector in the basis, and the second vector in the basis with alpha 2 and alpha 3 and alpha 4, and add them, you get this V. Those scalars, alpha 1, alpha 2, alpha 3, and alpha 4, form another vector, which is the coordinates of V with respect to this basis B. And this is what we want to find. And how would we do that? Given what you know of linear algebra, you would know what to do. You could write alpha 1 times this one, plus alpha 2 times that, plus alpha 3 times the third vector, plus alpha 4 times the fourth vector, equal to V, and you would get 4 equations, 4 unknowns, and you could solve it. But what we want to do is we want to think of this slightly differently. We want to say that, look, let S be the standard basis for this vector space. When someone tells you you're given this vector V 47, 2 minus 1, 8, what they have really given you is the coordinates of V with respect to the standard basis. And the question is that, how do we go from the coordinates of V with respect to the standard basis to the coordinates of V with respect to some other basis, a general basis B? Instead of having to solve that system of equation, is there a matrix that does the job for us? A matrix that will change the coordinate vectors from one basis to another, and that would be called the change of basis matrix. You have this basis and you have the standard basis. You want to know how to go from writing something in the standard basis in terms of B. And in fact, we want to do that in more general vector spaces. We have a vector space with 2 bases. How do we switch coordinates with respect to one basis to another? I could do this directly and not mention linear transformations at all. But the way I have decided to organize this topic is by focusing on matrices of linear transformations and thinking of these change of basis matrix, which we will define as an example of a matrix of a linear transformation. So let me remind you what a matrix of a linear transformation is. This was the subject of a previous video. So if you have 2 vector spaces and they're both finite dimensional, dimension of V is n and dimension of W is m, and you have a linear transformation going from V to W, then instead of the linear transformation, you can have a matrix. Start with a basis, an ordered basis for V, and you have an ordered basis for W. I don't actually need to know the elements of B, although if you know that, there's no harm in that. The matrix of T with respect to S and B is going to be the following matrix. Again, this is something that we have discussed in a previous lecture in detail. You start with V1, the first vector in the ordered basis for V, and you send that over, you find T of V1, and then you write that T of V1 in terms of B, in terms of the basis of the codomain. And then you go to the second basis element for the domain, V2, send that over, get T of V2, and write the coordinate of that with respect to B, again, the basis for the codomain, and you do that for all of them, and you will get a matrix that will have m rows and n columns, and that will be the matrix of T with respect to S and B. And what this matrix is good for is that if you have the coordinate of vector V, any vector in the vector space with respect to S, V is an element of the domain and you want to send it over. So what you do is that you write its coordinates with respect to the basis for the domain, and then you multiply it by this matrix of T with respect to S and B, and the result will not be quite T of V, but will be the coordinate of T of V with respect to B. And note that this matrix, even though I write it as bracket T, B, comma, S, I read it as the matrix of T with respect to S and B, because we're going from S to B. I'm going to apply that to a very straightforward, trivial example, and it'll become clear in the future slides why am I doing that. So let's say you have a vector space of dimension n, and you have a basis for it, again, an ordered basis for it, and you look at the identity map. The identity map is pretty trivial. It goes from V to V. It's a linear operator, and it just sends every vector to itself. So it doesn't do anything interesting. Let's ask, what's the matrix of the identity linear transformation with respect to this basis for this vector space? Because we're using the same basis for the domain and the codomain, we use a shorthand, and instead of writing the matrix of identity with respect to B and B, we write the matrix of identity with just respect to B. So what is that? And the answer is very straightforward. We do what we had said we do. You start with the first element in the basis for the domain and you send it over. Well, you send V1 over, you get V1. Then you have to write V1 in terms of B. So you have to find the coordinates of V1 with respect to B, but that's actually easy to do as well. How do you write V1 as a linear combination of elements in B? Well, V1 is in B. So to write it as a linear combination of elements of B, you just need one V1 and none of the other ones. You need one V1, 0 V2, 0 V3, and 0 Vn's. And so the coordinates of V1 with respect to B is actually just 1, 0, 0, 0. And that's going to be the first column of the matrix for this linear transformation. And then we do that for the second one too. V2 goes to V2 also. What's the coordinates of V2 with respect to B? And again, it's going to be 0, 1, and all zeros, because to write V2 as a linear combination of B, you don't need any V1s, you need one V2 and none of the other ones. And this continues. And so as you might have expected, the matrix of the identity map is the identity matrix, is the n by n identity matrix. And that's reassuring a little bit, but not really that illuminating in any way. What if we don't use the same basis for the domain and the codomain? We use different bases. What happens then? That's actually what a change of basis matrix is. Let me make the definition. We have a vector space of dimension n. We have two bases now, S and B. Both of them are bases for this vector space V. We have the identity linear transformation going from V to V. V is the domain, V is the codomain. We could have used the same basis for the domain and the codomain, but here we don't. And the reason is to be clear in the future slides. I'm going to use the basis S for the domain and the basis B for the codomain. Whenever you have linear transformation, and if you have decided on a basis for the domain and the codomain, you can replace the linear transformation with a matrix. And that matrix, it's going to be the matrix of the identity linear transformation with respect to S and B. And that's what's called the change of basis matrix. It will be called the change of basis matrix from S to B. And another name for it is a transition matrix from S to B. Change of basis matrix from S to B is the matrix of the identity linear transformation, a pretty trivial linear transformation, but when you're using basis S for the domain and basis B for the codomain. Let's look at an example, and then we're going to explore a little bit more what this matrix is and what it does. So let's say that you're in R3 and you've picked this basis -1, 2, 0, 2, -3, 2, -1, 1, -1 as your basis. And S is your standard basis. And you want to know what's the transition matrix from S to B. And you also want to know, what is this transition matrix good for? How do we do that? Well, the way we find the matrix of any linear transformation is you start with the basis of the domain and you send them over. So the first basis in S is 1, 0, 0. You send it over. Because it's the identity transformation, when you send it over, you just get identity. So what do you have to do then, though, is write the identity in terms of B. So what you have to do is you have to find the coordinates of 1, 0, 0 with respect to B. So I have to see, how do I write 1, 0, 0 in terms of these guys? And what I've done that, and you get -1, 2, -2, -4. So if you multiply the first vector by -1, the second one by -2, the third one by -4, and add them, you will actually get 1, 0, 0. If you don't believe me, stop the video and check. Then you do the same thing for the second element in the standard basis. Again, the place it goes is itself, and then then you have to take that basis element 0, 1, 0, but which is now the image of 0, 1, 0, and write it in terms of the basis. And I did that, and I get 0, -1, 2. And the same thing with the third one, and you get 1, 1, 1. And these are going to be the columns of your transition matrix, the column of the matrix of the identity linear transformation, but that's the transition matrix from S to B. So this is the transition matrix from S to B. And so Now we actually see how we do that. All we have to do is take these basis elements, or the S basis elements, and write them in terms of B basis elements and write their columns. And that's what the transition matrix is. But what is this guy good for? So, so again, I have the same information. S was the standard basis, B was this new basis, and the matrix of the linear transformation identity from S to B, or a better word for it, the transition matrix from S to B is given here. Now, what is that good for? So consider some arbitrary element, let's say particularly -3 of 1 -8 in R3. So identity sends this to itself. So what are we going to gain from looking at that? Well, what if we don't use the identity map, which would be the easier thing to do, but use this transition matrix to go from the domain to the codomain? Remember, the matrix of a linear transformation can replace the linear transformation. You can change, instead of plugging in a vector into your linear transformation and seeing what you get, you can multiply the coordinates by the matrix, and you will get the coordinates of the resulting matrix. So let's do that. So what does this matrix do? So let's see what it does. So the way you start is that instead of starting with V and plugging it into the linear transformation, you write V in terms of S, but that's actually just V. And then you multiply it by the matrix of the linear transformation with respect to S and B, and what you get is not the result I of V, which you would want, but you get the coordinates of that with respect to the basis for the domain. So this is what the matrix does. This matrix, this transition matrix that we found, this is what its job is. If you multiply V, the coordinate of multiply it by the coordinate of V with respect to B, you get the coordinates of the image with respect to B. Well, what's the image though? The image is V, so you get the coordinates of V with respect to B. So if you look at the beginning and the end of this, what we got is that what this change of basis matrix does is change coordinates. It's changed coordinates from S to B. You feed it a vector V. Well, you don't actually feed it the vector V. You feed the coordinates of V with respect to S, and out comes the coordinates of V with respect to B. And this is why it's called the change of basis matrix. It changes, it allows you to change bases, go from S to B, and does that by changing the coordinates of V with respect to S to coordinates of V with respect to B. And in this particular case, if you do that, we will get the coordinates of V with respect to B. So you take the matrix, multiply it by the coordinates with respect to S. In this case, it is the vector itself, because writing the coordinates with respect to the standard basis, you already have done that. You don't have to do any extra work. If you multiply it, you get the coordinates of V with respect to B. So now that you have this matrix, if you have other vectors in V and you want to change their coordinates from the standard basis into this strange basis, all you have to do is multiply by this matrix. So this matrix job is to change coordinates for you. Okay. Now what I'm going to do is I'm going to tell you 3 facts about change of basis matrix. And in fact, these 3 facts are the only things you need to remember. You actually don't need to remember how I defined it and where it came from. Because as I said at the beginning of the video, you actually can define change of basis matrix with no talk of linear transformations and their matrices. But that organizes things a little bit better and actually allows me to prove the various properties a lot easier. So V is a vector space and dimension of V is n. So S and T are 2 bases for V. So, and let's say that we have the change of basis matrix from S to B. So what can we say about this change of basis matrix from S to B? And the notation I'm using is the matrix of the identity transformation from relative to S and B. The first thing is that if S is V1 through Vn, then what is this matrix? This matrix is just you take V1 and send it over, but then you get V1. So then you write V1 in terms of B. That gives you the first column of this matrix. So in general, this matrix, the first column of it is just the coordinates of V1 with respect to B. The second column is the coordinates of V2 with respect to B. And the last column is the coordinates of Vn with respect to B. So this is what the transition matrix is. And in fact, I could have this change of basis matrix is, and I could have called this the definition. I've used this as a definition, but then I would have had to prove the other properties, which are not impossible to do and not that hard to do, but I like organizing them around linear transformations. So the second one is that, what does this matrix do? Because it's the matrix of a linear transformation, I do not need to prove this anymore. I know this, that what this does is that if you take the coordinates of V with respect to S and multiply it by this matrix, you get a coordinate of V with respect to B. And so the first property tells you what the change of basis matrix is. The second property tells you what it does. It changed coordinates from S to B. You feed it the coordinates of a vector with respect to S, comes out the coordinates of that same vector with respect to B. Now, the third property is actually very useful. It says that if you have the change of basis matrix from S to B, and then you find the change of basis matrix from B to S, those two are going to be inverses of each other. They're matrices, they're going to be inverses of each other. This last one I need to prove to you, and this is actually where thinking of this as linear transformations becomes really nice and elegant. But after I prove that, then I will look at a couple of examples, and the examples will show you how all three of these properties are useful. And again, this is the main theorem about change of bases. Okay, so now how am I going to prove that if you find the change of basis matrix from S to B and B to S, the two matrices are inverses of each other? Well, to do that, I want to remind you of composition of linear transformations and its relation to matrix multiplication. This is something that also was the subject of a video all by itself, where we talked about this in detail. But what we showed is that if you have a linear transformation going from V to W, V and W are vector spaces, and T is a linear transformation. And then you have another linear transformation L going from the vector space W to U. Okay, if you have that situation, you have an irresistible urge to compose them and find the composition of L and T, which I've been calling L circle T, which is the thing you get by starting, if you have a vector in V, you first apply T and then L, and then you get L of T of that vector V. Okay, but now what you want to do is you want to add bases. So these are vector spaces. So S and finite dimensional vector spaces of that. So S is a basis for V, B is a basis for W, and R is a basis for U. And as soon as you have a linear transformation and you have the two ordered bases, you can find the matrix of these with respect to those. So with T, you can find the matrix of T with respect to S and B, and that will be some matrix M. So M is the matrix of T with respect to S and B. Also for L, I can replace L with a matrix or come up with its matrix, and I'm going to call that N. N is the matrix of L with respect to B and R. And then the question is that, what's the matrix of L circle T with respect to S and R? And what we showed was that what you get, the matrix of the linear, the composition is matrix multiplication. This is sort of an amazing result. And actually, it's not so amazing because matrix multiplication was defined purposefully for this property to work. So when you compose linear transformations, their matrices get multiplied. That's all you need to know from here. And you could write that down algebraically, and that's sort of an elegant statement by itself. But now we can use it to prove that change of basis matrix going from one basis to another are the inverse of the one going back from the second matrix back to the first. So now I want to show you that proof, and the proof is really nice. So I start with the identity transformation, the trivial transformation that sends everything to itself, V to V. Okay, what am I going to compose that with? Well, I'm going to compose that with itself. Well, of course, I'm going to get identity. If you don't do anything, then you don't do anything. You haven't done anything. I mean, you probably have experience with that if you start the morning not doing anything and keep not doing anything, at the end, you haven't done anything. And so what? But now we're going to put bases. So I'm going to put basis S for V, and I'm going to put basis B for the second V. And for the third V, I'm going to have S again. Okay. So, and then I'm going to ask you, well, what are the matrices of this linear transformation with respect to these bases? Well, the matrix, that first matrix, is the transition matrix from S to B, the change of basis matrix from S to B, because it's the identity transformation. And the matrix of the identity transformation, we have given this new name, the change of basis matrix. What about the second one? Well, the second one is also a change of basis matrix. It's the change of basis matrix from B to S. But we had just said that when you compose two linear transformations, the matrix of the composition is the product of those. But what's the matrix of the composition? The composition is the identity transformation again, but this time from S to S. And that we saw right at the beginning that was just the identity matrix. So we proved that these two matrices, when you multiply them, you get the identity matrix. And therefore they are inverses of each other. You can write it algebraically also without the picture, but the picture makes it clear. This matrix, the transition matrix from S to B, I keep saying transition matrix, that's another way of saying change of basis matrix, from S to B is when you multiply it by the change of matrix from B to S, you get the matrix of the composition. But the matrix of the composition here, we know what it is, it's identity. So these two multiplied are identity, and therefore they're inverses of each other. And now we have all our three properties. Let's look at two examples. The first example is the example I started out with. So I have a basis for R4, and I have some vector in R4. I'm not going to actually do calculations, so let's just say some random vector in R4. And what I want to do is I want to find its coordinates with respect to B. So I want to write it in terms of these vectors and see what the scalars are that I need to write them as. Any vector in R4 can be written as a linear combination of these, but how do I find that coordinate vector? Well, you could do that by solving a system of 4 equations and 4 unknowns, but now we want to streamline that process once for all. So what we say is that, what we didn't think about is that we have a standard basis out there, and what we're given is the vector v, but that's the same as saying we were given the coordinate of v with respect to s, and what we want is we want the coordinate of v with respect to b. But the coordinate of v with respect to b, you can get from the coordinate of v with respect to s by multiplying it by the change of basis matrix. So where do I get this change of basis matrix? Well, if you think about it, what you have to do is you have to, how do I find that? Well, I have to take elements of S and write them in terms of B. And that might be a painful thing to do. And there's 4 of them. And you might say, well, if I had just one vector to write in terms of those 4, why would I want to write these 4 vectors in terms of those first? Well, you wouldn't mind doing that if your day job was finding coordinate of vectors with respect to B. You would once for all find the coordinates of these standard bases with respect to B, and that would give you the matrix, because those would give you the coordinates of the columns of that matrix, and then you could use that matrix all the time. But we can do a lot better than that, and how we can do a lot better is because of the fact that this change of matrix from S to B is actually the inverse of the change of matrix from B to S. That B to S was not the one we wanted, but it's easier to find. Why? Well, because how do I find the change of basis matrix from B to S? Well, I have to take the elements of B and write them in terms of S, but they're already written in terms of S, so I already have that, and so I can actually easily write that the change of basis matrix from B to S is just those basis matrices written as they are. Writing something in terms of the standard basis is actually very easy. So I write that, and then the next thing I have to do is I use that property and find its inverse. So I just feed this into some computer program and say, give me its inverse. And as soon as I know it's invertible because its inverse is the other change of basis matrix. And as soon as I have that inverse, then I plug it into I multiply it by v, which is the same as the coordinates of v with respect to s, and I will get the coordinates of v with respect to b. So that's how we use change of basis matrix. Let me give you a final example. This final example is about Legendre polynomials. So this is one polynomial. P0 of x is 1. P1 of x is x. P2 of x is 3/2 x squared minus a half. P3 of x is 5/2 x cubed minus 3/2 x. And P4 of x is 35/8 x to the 4th minus 15/4 x squared plus 3/8. These are the five Legendre polynomials, 0, 1, 2, 3, 4. So there's 5 of them. There's a lot more of them. This list continues. Legendre polynomials are useful in physics and in differential equations. And their definition, you can define them in different ways. You can define them recursively, or you can define them using differential equations. I'm not interested in those things where these come from. Right now, someone gave me these things. And what they wanted to know was that they had this other polynomial q of x, which is 1 plus x plus 1/2 x squared plus 1 over 1/6 x cubed and 1 over 24x to the fourth, a partial sum of the power series for e to the x. And what they want to know is that, how do I write qx as a linear combination of these Legendre polynomials? So I'm a linear algebra person. Someone has come and asked me this question. I'm not so interested in where these things came from. I want to help them write something as a linear combination of other things. That's what we do in linear algebra. So the way I'm going to think about it is that, well, there's a vector space in the background. What is that? Well, polynomials of degree less than or equal to 4. And there's the standard basis for that, 1x, x squared, x cubed, x to the fourth. But there's also this other set of polynomials, and these are also a basis. Why are they basis? Well, there's 5 of them. That's the right number because P4R is dimension 5. But not only there's 5 of them, they are linearly independent because none of them is a linear combination of the ones before, because every one of them has a new exponent term that the other ones do not, the ones before that do not have. So for example, P4 has x to the fourth, and none of the other the ones before that have x to the fourth. So you can't write it as a linear combination of the ones before. And so this list is 5 vectors in this vector space that are linearly independent. So it's a basis. And so what these are bases, and I have the coordinate vector of q with respect to s, because this was written in terms of the standard basis. The coordinate vector is just 1, 1, 1/2, 1/6, 1 over 24. And what I want is the coordinate of x with respect to b. I mean, I really want, and that's what I want. If I have that coordinate vector, I know exactly how to write q as a linear combination of Legendre polynomials. And so I want to change bases. I want to go from the coordinates with respect to one basis to another, and we just know how to do that. So what we want to use is that I want the change of basis matrix from S to B, and if I have that, I just will multiply by that column vector, which is the coordinates of qx with respect to S, and I will get the coordinates of qx with respect to B. And how am I going to find that? Well, I would have to write every element of the standard basis in terms of these polynomials. I don't like doing that. So instead, I will use the fact that that's the inverse of the change of basis matrix from B to S. And writing things from B in terms of S is actually very easy. So writing the change of basis matrix from B to S is just writing the coordinate. Every column is the coordinate vector of each one of these this one of polynomials written in terms of the standard basis, but they're already written. Like for example, P2x is 3/2 x squared minus 1/2. That means there's minus 1/2 of this one you need. You don't need any x's. You need 3/2 x squareds, 0x cubes, and 0x to the fourth. So that third column is the coordinate vector of P2x with respect to the standard basis. And I just read it off and write this down. After I've done that, I feed it into a computer and get its inverse. And then I multiply that by 1, 1, 1/2, 1/6, 1 to the fourth, and I will get the answer. So all you do to find the coordinates of qx with respect to b is multiplied by transition, to take that transition matrix and multiply it by the coordinates of qx with respect to s. But that transition matrix is the inverse of this other transition matrix, which is easy to find. This transition matrix is another name for change of basis matrices. This is the end of this lecture. See you at the next one.